Ladies and gentlemen, welcome back to Engineering Dynamics. In this video, we will be talking about the finite element method. And we will talk about the finite element method with regards to the videos that we did before, where we talked about the Rayleigh Ritz method. So how do we get from the Rayleigh Ritz method to the finite element method? This is just a very, very simple example regarding the finite element methods. And if you're interested in more videos, you can check out the videos I did about the finite element method more in detail. But let's propose again a system. So for example, we have a fixed beam. So it is clamped on this side and free on that side. And now we want to discretize our system. With the Rayleigh Ritz method, we proposed functions for the whole system. So we proposed some functions that might look like this. We proposed functions that look like this, and so on. But now we're doing a different step. So let me get rid of that. Now we discretize our system. So we cut out small pieces. For example, this is piece 1, then we have piece 2, 3, 4, 5, 6, and so on. And now we propose only functions for these elements. So this is where the element method, the element in finite element comes into play. We only look at one element, and we propose two special functions. So function 1 and function 2. So if we look at our element, let's get rid of that. So if we look at our element, the first function is 0 at the beginning, is 1 at the beginning, and the second function is 1 at the end. So this is where our functions come into play. And now we also, of course, are looking for the u, so the displacement, the time function, the function in time, sorry. So we can now do the same thing we did in the Rayleigh Ritz method, where we get a mass matrix and a stiffness matrix. Please have a look at the video where I talked about the Rayleigh Ritz method. And of course we have the G, so our forces in our element, and we have forces due to the load. So if we have a system, and these are our elements, one element can have a load, or basically the whole bar can have a load across the length, and reaction forces at the end. So if we look at just one element, we have some force here from the neighbor and some force there, and the distributed load. And now we can get the mass and stiffness matrix. And if we know that, this is our solution, where we have a stiffness for one element, and the mass matrix for one element. So we call that the elementary stiffness and mass matrix. And if we just have a uniform load P, we have this equation. This comes from the load, and these two are the reaction forces. Reaction forces from the element that comes from the left and from the right. We can use those equations, so the elementary mass and stiffness matrix, and combine them into one giant matrix. So we have matrix 1 and have matrix 2. So here we have, this is our system in general, but we don't look at that now. We only have two elements. So we split our bar in two elements. So we have displacement u1, we have displacement, u0, this is 0, u1, and here we have u2. So we don't look at that. And because we know Newton, we know that m times the acceleration, k times the stiffness is equal to the forces. And the same one goes for the second element. But now we have a lot of equations for too many unknowns. So we have the unknowns here, 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 and there. So we have 4 unknown reaction forces, and we have 4 unknown displacements. And now we need to work with the boundary conditions. The first step is to see that the displacement of our first element and our second element, so these two, this must be the same. So we say that u2, so the second displacement of element 1 is equal to the first displacement of element 2, or in this case, the acceleration. And here we have the displacements, because if they're next to each other, they have the same displacement and the same acceleration. Then, of course, we have the forces. So a force here and a force there. on each end of the node. And we say that, well, they must be 0 because if this point is not moving or not relatively moving, they must have the same forces on that node. So this is why we have P21 and is equal to minus P12. So we combine those two equations. So we reduce our vector u dot, and we shifted those two matrices. Let's have a look here. We shifted those two matrices to the right and to the left so that the dimensions add up again. So we have 3 by 3. Then we say that, well, the reaction forces are equal. So the reaction forces are here. So we again removed one or two unknowns. So these are equal. And the last step to do, we said that they are equal. So we added these two equations. So we had this matrix, and this matrix is now shifted down, and this matrix is shifted up, where these two now overlap. So this is how we get these overlapping matrices. But now we still have too many equations and too many unknowns. The only thing that we didn't consider so far is that we know the displacement of our first point. So if we have a free bar, let's say right here, so we have a displacement, a bar, and we said that the left side of our bar is fixed. So we know that u is equal to 0. And here, if u is equal to 0, the displacement is equal to 0. So this will be all 0, and this will be all 0. But now the dimensions, if we remove that part, the dimensions don't fit anymore. So we will say that, well, for now, we just ignore the first equation. We ignore the first reaction force because we are more interested in the displacements for now than in the reaction forces. So this is how we are left with a 2x2 system with the stiffness and mass matrix and our forces and one reaction force at the end that we can, this is the force at the end of the bar. So this is n dash, better to say, because this is known. And what we are just basically left, or how we got there is to these equations, is basically an overlap of those matrices where we said that u is fixed, so it is 0, and we eliminated the row, the first row, and the first column. And this is how we got from the Rayleigh Ritz method to a element-wise view where we proposed two functions. And we said that we now can get the mass matrix and stiffness matrix, which we call the elementary mass and stiffness matrices. And then we combined them all into a giant system. Then we said, well, we know that the displacements must be equal and the reaction forces must cancel out. That's how we got to this system. Then we said, because we know that our u is 0, we can eliminate the column, the first column, and eliminate the first row, thereby eliminating our reaction force. And then we only are left with two equations for two unknowns, because P2 will be our given force. And that's how we can solve for the displacement of a system that we discretized. And the more elements we use, the more correct our system will become. I hope this video gave you a very basic introduction to the finite element method. To understand it, you really have to watch the Rayleigh Ritz method video. If you have any questions, feel free to ask them in the comments down below, and I'll see you next time. Thank you very much.